Hi, George Diamond here. Now today we're going to be looking at some velocity acceleration graphs on this video. We're kind of reviewing a little bit. My students have been working some in our AP Calculus class. We've been working a little bit with velocity acceleration. In this video and in video number 2 now we're going to look at some actual examples, some actual problems. Now today we're going to take a look at some velocity acceleration graphs. We'll take a look at a position graph and a velocity graph. Now let me put I've got a tire pump here, so let me put my tire pump out of the way. Now this really isn't in our textbook so much. In our textbook we use the Larson text, and there's some velocity acceleration questions in just about every section that we look at. So we're going to kind of be focusing on velocity acceleration in this video and the next video. But we want to start off, so we'll be looking at a couple graphs in just a second. But first, let's see if we can review a little bit about velocity acceleration. And like I said, my students have been working with velocity acceleration a little bit as we've looked at derivatives. All right, so a little bit of a review is in order here. First of all, S of t typically represents our position function. So like I said, my students have already know that, but still, I want to go ahead and point this out. So S of t represents the position function of a particle, and mainly in this video and the next video, we're going to be looking at several problems involving particle motion along a line. So either along a horizontal line or maybe along a vertical line. But S of t represents the position function, and my students will remember that the first derivative, the derivative of the position function, gives you the velocity. Right? So that'll describe the velocity. All right? Now, if you take the derivative of the velocity, what would be the second derivative? Right? That's going to describe the acceleration. So the second derivative describes the acceleration. Okay, also another thing we need to remember about velocity acceleration is speed. Right? Now speed is the absolute value of velocity. So speed can't be negative. Now velocity can be positive or negative depending upon whether a particle is moving to the left or to the right, or up or down. So depending on the direction. But speed, direction doesn't matter. All that matters is simply the speed is simply the absolute value of velocity. So you can see this here. So let's go ahead and take a look at also what's called the generic projectile motion equation. Now students that have taken physics may be more familiar with this than some other students. But let's say S of t. So here's our position function. This is so the position of an object, or maybe a free-falling object, is equal to -1/2 g times the time squared plus v sub 0 times the time plus h of 0. Now in the generic projectile motion equation, now the reason I'm looking at this is because sometimes with velocity acceleration problems, you may have to write your own equation, okay, given the information, certain information. Now first of all, in the projectile motion equation, g represents your gravitational acceleration constant, either 32 feet per second squared or 9.8 meters per second squared. All right, something like that. V sub 0 on the linear term here, so V sub 0 represents the initial velocity, and h of 0, the number down on the end, represents the initial height. So if you're dropping an object off a building, that would be a projectile motion problem. And once again, g is your gravitational acceleration constant, either 32 feet per second squared or 9.8 meters per second squared. V sub 0 represents your initial velocity, h of 0 represents the initial height. And like I said, students that have had any physics, they've probably done quite a bit of work with this projectile motion equation before. Now, one thing that my students need to pay close attention to, we've not looked at how to tell when a particle is speeding up or slowing down. All right, now, to tell how, you have to analyze the velocity and acceleration. So first, okay, if the velocity and the acceleration have the same signs, okay, then a particle is speeding up. Right, so you got to go look at their velocity and acceleration at a particular time. So if the velocity and acceleration have the same signs, then the particle is going to be speeding up. So if you got a positive velocity and a positive acceleration, okay, or a negative velocity and a negative acceleration. So they can both be negative. Velocity and acceleration can both be positive. If that's the case, then your particle is speeding up. Now my students, at the end of the year, they'll be taking the AP Calculus exam, and there's, quite often you see problems with you'll have to describe and tell whether a particle is speeding up or slowing down. And And to tell which, now you have to be able to tell whether the velocity is positive, or negative. If they got the same signs, then the particle is speeding up. Now, if the velocity and acceleration have opposite signs, so they have opposite signs, then the particle is slowing down. So it has opposite signs of slowing down. So if the velocity is negative, the acceleration is positive, it's slowing down. If the velocity is positive and the acceleration is negative, the particle is slowing down. So if they have opposite signs, the particle is slowing down. If they got the same signs, the particle is speeding up. Now, in the next video, we're going to do a problem. So we're going to look at an actual problem where to tell whether or not the particle is speeding up or slowing down. Now let's take a look at a couple of graphs. So we'll look at a position and a velocity graph. All right, over time. Here's our first. Let's start off with two what we call obvious observations. All right, so this pretty much goes without saying, but I'm going to say it anyway. Number one, the motion to the right or up is positive, right? And motion to the left or down is considered negative. So remember that? So let's start off with a position graph. So this, you can imagine this could be a particle moving along the x-axis or along a coordinate axis, right? Either a horizontal line or a vertical line over time, right? So here's our graph. Right, now you can see the graph is composed of 1, 2, 3, 4 line segments. Right? And you can see now we have a particle at time 0, the particle is at 1. After 1 unit of time, the particle is at 1/2. So from 0 to 1, the particle is moving to the left. Right? And then at 1, it changes direction. So the particle moves along a horizontal line. So this is a particle moving along a horizontal line. The graph above shows its position as a function of time. So, a couple of questions about this graph that we want to look at. So, a couple of questions. Number one, when is a particle moving to the left? So, when is it moving to the left? Now, well, I said in a position time graph like this, it's moving to the left. The particle will be moving to the left when the slope of your line is negative. Right? So, you notice from 0 to 1, the particle starts off at 1. After 1 unit of time, it's at 1/2. So it's gone from 1 to 1/2. So the particle is moving to the left from 0 to 1. And then it changes its direction. Then it starts moving from 1 to 3. The particle is moving to the right. So when is the particle moving to the left? It's moving to the left from 0 to 1 and from 4 to 6. So the particle moves to the left when the graph has a negative slope. Right. And that would be from 0 less than t less than 1, and from 4 to 6. Right, so two intervals there which the particle is moving to the left. Right, so that's our first question, when's the particle moving to the left? Next question about our graph. Okay, when is the particle standing still? All right, now obviously you can tell that from between 3 and 4, you can see the position doesn't change. So between 3 and 4, the particle is standing still. And I'm also going to add, I didn't put this on the PowerPoint, but it would be standing still at t equals 1, right? So it's moving to the left and then it changes its direction. So when it changes direction, it's going to have to stop for just an instant. So it would be standing still at t equals 1 also. So the particle standing still when the graph when the graph is horizontal with the slope equals 0. And that would be between 3 and 4, and I would add also at t equals 1. Right, so at one unit at a time, it's standing still because it changes direction. Okay, number 3. Okay, when is the first time p reverses its direction? Okay, well, that would be at t equals 1. You can see it's moving to the left and then it starts to move to the right again. So you have a negative slope, so it starts off at 1. After 1 unit of time, it's at 1/2, so it's moving to the left. And then from 1 to 3 units of time, it goes from 1/2 to 2, right? So now it's moving back to the right. So it reverses its direction at t equals 1. So p changes direction at t equals 1. That would be the first time. Okay, next question. Okay, when does p move at its greatest speed? Right, now let's see, at its greatest speed. Now this is a position time graph, so the velocity would be the slope of each line segment, right? And the greatest slope would be where you have the steepest line, right? And that would be from 4 to 6. So that's when it would have the greatest speed. It would have the velocity would be negative, but still the speed would be positive. So between 4 and 6, okay, the graph has the steepest slope, so that would be when it has its greatest speed. So just a little look at a position time curve, or position time graph, if you will. So like I said, students that have maybe taken physics, they've have worked with these types of graphs before, I'm sure. Okay, let's take a look at another type of graph. Now the second type of graph is a velocity time graph, or a velocity time curve, if you will. So let's look at a couple questions involving the velocity time graph. Now, here's my graph. Now my velocity time graph is composed of 3 line segments. You can see the 3 here. Okay, over 6 seconds. All right. And a couple questions now. You can see velocities on your y-axis over time, so the velocity over time. And this particular graph is described as a particle moves along a horizontal line again. Okay, the graph above shows the velocity as a function of time. Now, a couple questions about this graph. And there's lots of stuff we can do with it, but I'm just going to ask a couple questions. Okay, first thing we noticed here says, when is the particle moving to the left? So when is this particle moving to the left? Now, you look at your velocity now. If the velocity is negative, the particle is moving to the left. If the velocity is positive, the particle is moving to the right. So as you look at your graph here, okay, right here, at 1 and 4, you can see it starts off at 1, so the velocity is positive from 0 to 1, so you have a positive velocity, and then it goes below the x-axis, and the velocity is negative, and then positive again. So the graph is going to be moving to the right, and then to the left, and then back to the right again. All right, so then back to the right. So it's going to be moving to the left from 1 to 4. This is when basically when your velocity curve goes below the x-axis. Okay, that would indicate a negative velocity. So between 1 and 4, right, the velocity is going to be negative. So P is moving to the left, okay, when the velocity graph has a negative value. So that would be between 1 and 4. Okay, next question. All right, so same graph, next question. Okay, when is P standing still? Well, the particle is going to be standing still when it changes direction. And you can see it changes direction at 1 second, at 1 unit at a time, and at 4 units of time. So it's moving to the right and then to the left, so it's going to change at 1 and 4. So when the velocity graph has a 0 value, right, so that would be at t equals 1 and t equals 4. So those will be where it changes direction. So as it changes direction, it has to stop for just an instant, and then it'll move in the other direction. Now, second question about our graph. When is the first time that the particle reverses direction? Well, that would be at t equals 1. So P changes direction the first time at t equals 1 unit. All right, so it changes direction here. And you can see the particle moving, it says moving to the right, and then it starts to move to the left at 1. Okay, next question about our graph. When does P move at its greatest speed? Now, speed, remember, is the absolute value of velocity. So let's see, you notice this looking at the graph here, at t equals 0, you can see the velocity is 1. Right? At t equals 2, after 2 units of time, the velocity is at negative 1. Right? And you come all the way down here to the other end point now. At t equals 6 units of time, right, the velocity is at 2. Right? And the absolute value of 2 is 2. So the greatest speed here would occur at the end of the graph. So P moves at the greatest speed at t equals 6. Okay, since that is when the velocity achieves its greatest absolute value. Right? So at t equals 6, the velocity would be positive 2, and that's when it achieves its greatest absolute value. Let's see, I think we have one more question here. Let's take a look at the next question. So one more. Let's see if we can write a piecewise function for the acceleration. Now this is our velocity. This is our velocity graph here. Now acceleration is the derivative of the velocity. Now when we talk about the derivative, we're talking about the slope of each line segment. So down at the bottom, I'm going to start my piecewise function. Now you got to do this in parts because you have 3 different line segments. You're going to take the slope 3 times. Now you notice from t equals 0 to t equals 2, you can see the line here has a negative slope. So we're moving to the right and then down. So let's see, now we're moving to the right 2 units, and then we're moving down 2 units, so it'll be -2. So on the interval from -1 to 2, we say the slope would be -2 over +2, which is -1. So the acceleration would equal -1 on the interval from 1 to 2. So when we start our piecewise acceleration function now, we'll start it off like this. On the first interval from 0 to 2, the slope is -1. Now, so the slope is -1. Now, on the next interval, okay, from 2 to 3, you can see we've got the slope equals 0. And that means the acceleration is going to be 0 also. On the second line segment there from 2 to 3. Now keep in mind the velocity here has a corner at 2 and 3. So the derivatives of the velocity, the derivative wouldn't exist at each of your corners. So it'd be 0 from 2 less than t less than 3. That would be our next interval. And then the last line segment from 3 to 6. Right? So from 3 to 6, this would be, let's see what our slope would be. Now we're moving to the right 3, and we're going up 3. Right, so our slope is equal to 3 over 3, which is 1. So the acceleration on that last line would be 1. All right, so the last part of our piecewise function would be 1 from 3 to 6. Now I'm going to put that it's going to, so the endpoints here would be included, so it'd be 0 less than or equal to, and it's be less than or equal to 6 on the other end. So three parts of our piecewise acceleration function. So it's going to be -1 from 0 to 2, from 0 less than or equal to 2, then 0 from 2 to 3, and then 1 from 3 to 6. So this is our piecewise acceleration function. This is how you have to do it. So with a line segment like this, you're basically talking about the slope of each line segment, because remember the acceleration is the derivative of your velocity. Derivative is slope, so you're going to have to figure out what the slope of each line is. Now, in our next video, we're going to do some actual problems where we actually determine where we're given a function, what happens with a particle moving along a particular line. Right?